Today, this is kind of an adventurous talk because I don't know what about invariant theory you should really know. So I'm going to say a bunch of things, and we're going to get some heckles from Avi telling me that I've not said certain things. So I have a flexible plan, which means at some point I'm going to forget my notes. So feel free to ask me whatever questions you want. Okay. So here's the plan. First, I'm going to talk about this problem of bipartite matching that all of you should be somewhat familiar with. And I'm going to pull out some features of it that look like invariant theory. And then I'm going to go tell you the basics of invariant theory and certain finite groups and infinite groups and so on. Okay. So what is this problem of bipartite matching? It's bipartite perfect matching. So this is the problem. It's an algorithmic problem. And it says decide if a given bipartite graph which I'm going to label gamma has a perfect matching. Everybody knows that this has a polynomial time algorithm. It's not a secret, but so here's what it looks like. Somebody gives you a bipartite graph. I'm going to label the edges 1 to n on both sides, and it's going to be a bunch of I'm going to label the vertices by 1 to n on both sides, and there's going to be some number of edges between them, and you want to know if there's a perfect matching. I don't have to explain what a perfect matching is. So what you do is given this bipartite graph, I will construct what I call the adjacency matrix, or if you like, the bi-adjacency matrix. It's an n by n matrix. So it's an n by n matrix, and you put a 1 in the ijth spot. If there's an edge from I to j. Is that clear? This matrix is not symmetric. Yeah, just to be clear. Okay. Now I'm going to make a claim, and let's see how obvious this is. I say gamma has a perfect matching if and only if the permanent of this adjacency matrix is non-zero. Let's think about what a matching here is. A matching here is basically a permutation, right? And that permutation corresponds to one of the things in the permanent. The permanent is a sum over permutations. Yeah. So this guy here. So let's say you had a matching here, which was so you have a matching that goes 1 goes to sigma 1, 2 goes to sigma 2, n goes to sigma n. This corresponds to a certain monomial that looks like right? And the permanent is a sum of such things. And really, not just is this, there's something much stronger here. This, whatever this number is, it counts the number of perfect matchings. Is that clear? Okay. Now I'm going to tell you something else about these things. So in particular, I want you to think about these monomials here. The permanent is really not that important in this setting. It's these monomials that are important. And what I'm going to do is I'm going to tell you that these monomials are invariant for a certain action. So let me tell you what the group is. So I'm going to define a group for you. It's not a finite group. It's an infinite group. So it's the group of diagonal matrices such that the product of the diagonal entries is 1. My first claim is this is a group. If you multiply two such things, you get another such matrix. The inverse of such a matrix is again such a matrix. Okay. So the group that I'm going to talk about here is going to be a direct product of two copies of this. And I want to say it acts on the vector space of, let me not try this, it acts on n by n matrices. Okay, I have to tell you what the action is. The action is this. So if you have two diagonal matrices, one in each one of them, and you take some matrix X, it sends it to D1, X, D2. Okay, I'll be more clear. If so if this matrix were A1 to AN, okay, that's not the way to write it. So let me write this out in coordinates. If D1 was A1 to AN, and then you multiply with X, and then you multiply with B1 to BN, all you get is a matrix whose ijth entry is AI, Bj, Xij. Okay. Let's hold that group action. And now I want you to observe that such a group action will leave such a monomial invariant. Okay. Let's see how. So let's take this monomial x1 sigma 1, xn sigma n. And now let's see what this is doing, right? So this particular action is sending xij to ai bj xij. Is that correct? So when I do this action, when I act by d1 comma d2, this one is going to a1 b sigma 1 x1 sigma 1. Yeah, and then a2 b sigma 2 x2 sigma 2 and so on. An b sigma n xn sigma n. Okay, I pull out all the scalars to the front and I get product of ai, product of bi into the original monomial. And this is 1, right? By definition of what this group is. Okay. Now let's do something a little bit more fun. Let me pick a particular nobody here. Let me pick a particular bipartite graph, and the bipartite graph I'm going to pick is this. Does this have a perfect matching? No. Okay. What's an easy way to see this? This is my bipartite graph. This is my graph gamma. I look at this adjacency matrix, and I tell you that this adjacency matrix looks like this. Okay, and I want you to focus on these 4 zeros. So there's this big block of zeros that's preventing the permanent from being non-zero. Do you see why that is? If you have such a big block of zeros, no matter what the other entries are, the permanent or the determinant will all be 0, because there's no way you can get a particular monomial to have non-zero entries on all of the coordinates, right? Yeah. In this language, this is Hall's theorem. Okay. Hall's theorem is telling you that what is it telling you? That a certain set has smaller neighbors than it should. What's such a set here? It's 1, 2 has smaller neighbors than it should, and that corresponds to 1, 2 and a big block of zeros here. that make sense? Okay, so that's the vague idea. But now let me give you a different, let me do a computation. Okay, I'm going to do a computation that's going to look a bit strange. So let me see where I want to do this computation. Okay, I'm going to do a little computation that's going to look a bit strange, but it has something to do with the group action. So okay, so I'm going to take a 3 by 3 diagonal matrix that looks like this, and my claim is if you put in any number for t other than 0, this is actually going to be in ST3. The product is 1, right? And then I take a second such a matrix, and this time I want t squared, t inverse, t inverse. Okay, the same thing. Now what happens if I multiply this adjacency matrix on the left with d1 of t, on the right with d2 of t? Okay, so let's figure out what happens. Well, we know what happens, right? We just have to multiply the ijth entry with the corresponding thing here and the corresponding thing there. And if you do it, my claim is you're going to get t to the 4 t, and I'm going to write this block of zeros with something in there. Which is equal to t to the 4, t to the 4. Yeah, does that make sense? Okay. Now what happens if I take limit t goes to 0? Then this matrix vanishes, right? Okay. So that's the phenomenon that I wanted to show you. And now let me describe what it really means. Okay, by the way, so first, do you believe that if you picked any matrix with this big block of zeros, you could come up with similar looking matrices d1 and d2 to do this? Do you believe this?
What does it mean, similar looking?
Well, you have t to the power something here.
And the goal would be to get something
that goes to 0. Yeah, the goal would be something like this. Yeah, you believe this? Sure. Okay, so what I'm going to tell you is, what did I do? I took, so this was basically the action of d1 of t and d2 of t acting on a gamma, right? That's how I define the action. So what I said was, I'm going to take elements of this group ST3 cross ST3, and I'm going to drive your adjacency matrix down to 0. And I'm claiming you can do this if you don't have a perfect matching. And the claim is, if you have a perfect matching, you cannot do this. Do you see why you cannot do this? Yeah, you see? Because this particular monomial you can't drive down to 0. It's invariant under the group action. Okay, so that's the dichotomy. So the dichotomy is, you have gamma. If it has a perfect matching, then some monomial, when I say monomial, I mean monomials that look like this. Now maybe I should say permutation monomial. Is not equal to 0. And if it doesn't have a perfect matching, can drive a gamma to 0 in the limit by group action. Yeah, all these statements are self-believable with enough evidence. Okay, this condition here is what is another way of phrasing that A gamma is in the null cone, which I have not defined for you, but that's roughly the definition. Okay, so
null cone of this matrix is.
I have to tell you what the null cone is. It's a null cone for the action. Okay, I have to define for you what the null cone is, but I just want to make a little conclusion, basically that gamma doesn't have a perfect matching if and only if A gamma is in the null cone. And so what really happens is this problem of perfect matching is a special case of what you would call null cone membership. Okay? And this null cone membership is exactly what you think it should be. You have a group acting on some vector space. You have something called the null cone that I will define for you in a bit. And given some element of the vector space, you ask whether it's in the null cone or not. Okay? And you can see there are two ways to go about it, right? First, how do you prove that something is in the null cone? You can prove something is in the null cone by driving that thing down to 0 using the group action. How do you prove something is not in the null cone? Okay, so what is this permutation monomial here? This is what I wanted to say invariant, right? You show some invariant of this action, which takes a non-zero value on your at the point you're looking for. Right? So there are both ways to do it. Now, of course, if you are a complexity theorist, you would ask, what is the complexity of doing either of these things? Yeah? Okay. Cool. Now I have no choice but to tell you a little bit about the basics of invariant theory, because otherwise I cannot define for you what a null cone is. As always, if you don't understand any particular definition that I make, you have to stop me, because I won't know. So, this is just going to be the basic setup. Okay, you can do more general stuff. You can work over all kinds of fields, whatever it is. I'm going to take the most simplest setup to try and get the problems across. So, my underlying field is always going to be the complex numbers. So V is a vector space over the complex numbers, let's say finite dimensional. Now, I denote by CV the polynomial functions on V, which nobody likes. So if you think of V as an n-dimensional vector space, then polynomial functions is just going to be polynomials in n variables, right? And why do I call them polynomial functions on V? Because any polynomial in n variables you can think of as a function on V. And what kind of function is it? It's a polynomial function. Okay. Cool. And then the setup is, of course, that you have a group acting on this vector space. Don't think too hard about what kind of groups at the moment. What is a group action? A group action I like to think of in two different ways. One is it's a group homomorphism from G to GLV, and the other is that it's a map from G cross V to V. Okay. And when I write G cross V to V, I'm going to write the image of G comma V to, this is sort of shorthand. Okay. So what does it mean for a group to act on V? It means given any element of the vector space and an element of the group, it's going to take it to some other element of the vector space. How is it going to do it? It's going to do this by some linear transformation. Okay, so I'm talking about linear action. Which linear transformation? The image of whatever it is here. Okay? And the basic way I said it before, you have an element of the group, you have an element of the vector space. It's going to take it to some other element of the vector space. That's the way to see both of them. Okay? Here I don't have to tell you any conditions. Here I have to tell you some conditions because any such map cannot be a group action. Okay? And the condition here is just going to be G acting on H acting on V is G times H acting on V. And of course, identity takes V to V. Everybody somewhat familiar with group actions? Yeah, just
I know a group which is like from 8 properties, like but let's say a finite field which satisfies this property. So what, like, how should I understand a group action?
okay. So this is because you've been taught groups badly. You should always think of you should always learn groups from their actions. Groups are by sort of definition groups of symmetries. Okay, so you have some object in nature. It doesn't matter what. It could be a field. It could be a vector space. It could be some what are these things called? Dodecahedron, icosahedron, whatever it is. And you look at the symmetries of such an object, and they have certain features. What are the features they have? You can compose two symmetries. You can take the inverse of a symmetry.
Okay, so it's just the operation which takes two numbers and
Yeah, so it's a symmetry. So the group is acting on this.
Okay.
Thing. Okay. We'll see some examples. Everybody is familiar. Yeah.
The vertices of a graph and therefore permitting the edges. That's the one classical.
Okay.
I think we see.
Right. The symmetric group should be familiar. The cyclic group should be familiar. The group of invertible linear transformations should be familiar. If you've done change of bases and change of coordinates in linear algebra, that's an action. Okay, I got a bit sidetracked. So we
linear on the right somehow?
what?
Is there some condition based on the right?
Yeah, I'm asking for it to be linear. Yeah. What's the easiest way to say it? There's no good way to say it. Basically, what Jeroen is telling me is that if I look at this map and I fix an element of this group, then I just get a map from V to V, and that should be linear. Let's not bother with that. Okay. So if you have a polynomial function, I call it invariant if it doesn't see the group action. Is that a good enough definition? Okay. So I'm going to define something else that makes it slightly easier for me. I'm going to define the orbit of some element in my vector space. Okay, which is all the points that you can send it to with the group action. Okay. So a function is invariant if it's going to take the same value along every point of a certain orbit. Yeah, it doesn't distinguish between 2 points of the orbit. Okay, so this thing is sometimes said as a constant along orbits. Okay, and you look at the collection of all invariant polynomials. And it because if you add two invariant polynomials, it's going to be invariant. You multiply two of them, it's going to be invariant. Okay, so this is a subring of the ring of polynomial functions. Okay, so let's do some examples. And I go back to the first example that really started this whole subject. And here, the vector space is going to be degree 2 forms in 2 variables. Let's say the 2 variables are x and y. Okay. So what is a degree 2 form in this? It's just something that looks like ax squared plus bxy plus cy squared where A, B, C are in complex numbers. Huh? That's what I mean by degree 2 forms. It's a vector space. It's a 3-dimensional vector space. Okay. Now on this, there's an action of the group SL2. Okay. This is 2 by 2 matrices with determinant 1. How does it act on this space? It's maybe not entirely obvious, but really I will tell you how it acts on this space. If you have such a matrix, just do matrix vector multiplication with x and y, and you get px plus qy, rx plus sy. Okay. And so if you want to know how this matrix acts on this guy, plug in these two for x and y. Okay. So the action is defined as PQRS acting on this particular thing is A times Px plus Qy whole squared plus B times Px plus Qy into Rx plus Sy plus C times Rx plus Sy squared. Can someone tell me an invariant for this action? It's something that you know. You might just not know that it's an invariant for this action.
If you write a matrix like A minus B half C, then the determinant of this matrix is.
Yeah. Okay. So what Andre is telling me, which I'm going to rephrase, is there is this thing called the discriminant that we know. Okay. And the claim is the discriminant is an invariant function for this. So let me tell you what exactly it is you have to do to check this. Is okay, you have to write this again as something times x squared plus something times xy plus something times y squared, right? So you rewrite this, you get a prime x squared plus b prime xy plus c prime y squared, and this a prime, b prime, c prime are going to be something in the a, p, q, r, s. Right? And then you have to basically check that b prime squared minus 4a prime c prime will simplify to b squared minus 4ac. Okay? You have to check this. And you do have to use at some point the fact that this is a matrix of determinant 1. So you will have to use that p times s minus r times q is 1. Otherwise, you won't be able to get that. But this has a geometric meaning. What is this discriminant? When do we see this discriminant? We see it in the quadratic formula, right? And so if the discriminant is equal to 0, what does it mean? It means that both roots are the same. Yeah? And that should be a property that's invariant under change of basis. Okay? So the whole point of invariant theory back in the 19th century was to say that when you have these kind of geometric properties that are invariant under change of basis, you should be able to describe them by polynomials that are invariant. Okay? Let me give you another example that's a pseudo example. Have you all seen Mobius transformations? So this is you take a complex number and the transformation goes, let's go, pz plus q over rz plus s. Are people familiar with Mobius transformations?
You should say that this is an action of SL2.
Well, I was, yeah, it is.
But you wrote the letters, I'm not sure that it was.
Well, it's not an action. It's a bit more complicated. So, but are people familiar with Mobius transformations? Never? Okay. So these are precisely the transformations that go from complex numbers to complex numbers that preserve angles. Okay? They're also called conformal maps. And the cool thing about these transformations is if you have 4 points, and you want to know when these Mobius transformations can send them to a different set of 4 points. Yeah, this is a very geometric fact. It's saying if you have 4 points and you try these maps that preserve angles, can you send them to a different set of 4 points? It happens if and only if the cross ratios are the same. I guess there's more than one cross ratio, but they're all kind of equivalent.
Sorry, are there any restrictions on PQRS?
Yeah.
Determinant as well.
Yeah.
Same deal.
Yeah. Now, why I call this a pseudo example is that what I've written for you is not a polynomial. It's a rational function. Okay, so that's another way you can go forward in the subject that I'm not going to pursue. Is you can also look for rational invariants and so on. Okay, another way you can loosen it is you don't have to look at you can take any other thing that you like that groups act on. You don't have to look at polynomial functions. You don't have to look at rational functions. You can look at whatever functions you want. Okay, but at the end of the day, there's in algebra which says if you want to separate two objects, when you say separate two objects, you mean two objects are not isomorphic. You find some invariant that differentiates them. Okay? So you might want to think of group actions as in such a way that orbits basically tell you what equivalence classes are, and you want to separate equivalence classes, and you do it by functions that are invariant. Sorry?
So not always polynomial, sometimes rational.
It could be whatever you want, right? It doesn't even have to be polynomials. It could be cohomology. It's just a philosophy. Yeah, it doesn't have to be true, right? In some cases, we don't know how to do these things. Let me see, it's a little past 11. So now I'm going to talk about finite groups, and I'm going to do some examples, and I want to do some computations with you so that you get a feel for it. Okay. So the first group that I'm going to take is the one Okay, so if you want to prove something like this is finitely generated, right? So what does Hilbert do? He says, just look at all the invariant polynomials. It's an infinite collection, but it generates some ideal, because all ideals are finitely generated. That's what Hilbert proves. You take the generators of that ideal, at least in a specific form, and those will be generators for the invariant ring.
That's another thing you need to prove.
That's another thing you need to prove. That's sort of an inductive argument where you look at the lowest degree, of course they have to be invariants, and then you keep going further and further. Okay? But where is this finite generation coming from? It's coming from ideals of being finitely generated.
And then you need to be algebraically closed.
Yes.
Which ideal?
Okay, let's do this. My claim is first that invariant rings are graded. So if a certain invariant polynomial is if a certain polynomial is invariant, then each degree is invariant. Okay, I claim this. And now what I want is I want to take the ideal that's generated by the union
The ideal in the polynomial ring.
in the polynomial ring.
This ideal will contain non-invariant things also.
Yes, it will.
Okay.
It will contain non-invariant things. But somehow the generators of this ideal are enough to pull out the generators of the invariant ring.
The generators can be invariant.
Yeah, 2 steps.
Why would it contain non-invariant?
Ideals are kind of silly, right? Ideals are kind of silly in the sense that you can multiply with things that are not part of. You could just take an invariant and multiply with x.
Oh, okay.
It will just never be invariant.
Actually, this is the silly thing that I wanted to say about it.
Okay.
So if you took like a standard algorithm, going to basis or something, or even, I mean, how hard is it to do the last step?
Which step?
To show that from the generators of the ideal, it might not be invariant, you get,
No, okay, so there's one way to do this, right? Okay, you have this ideal. It's given in terms of generators which are all invariant. If you go degree by degree and prune out, you will be able to find generators that are all invariant for this ideal. So you can find a set of generators for this ideal which are all invariant in a very standard fashion. Look at the smallest degree. Okay, those are all invariant anyway. Then you go to the next degree and you prune out whatever came from below, and then you take out whatever's left. Okay, so you can do this so that you get a set of generators that are all invariant, and then you have to prove that this will actually generate the ring in the other sense. Okay, so there are two things that I want to point out here. The first is there is this thing called the Reynolds operator, which we've seen before in finite groups. So in the case of finite groups, it's basically this: you take some function and you just take all translates of that function. Right? This is how we generated symmetric polynomials. This is how we generated these cyclic polynomials, or whatever it is. Okay? And the claim that we made for finite groups is that this is actually a surjective map. We said every invariant polynomial can be got in this fashion. Okay? So this thing is called the Reynolds operator. Okay? And okay, we know such a thing exists for finite groups. But one way of defining reductive groups are precisely those groups for which Reynolds operators exist. Okay? It's precisely what will let you prove something along Hilbert's lines. Okay, so here's one theorem that I want to state. This is a theorem of Emmy-Noether, and this is for finite groups. So G is a finite group, and it's acting on a vector space. Then the invariant ring is generated in degree at most the size of the group. It's a non-trivial theorem. It's one of Noether's famous, one of the more famous theorems of Noether. In positive characteristic, you have other issues, which I won't tell you about. But now you know why I stopped at degree 3 there. Okay? So this process that we did, we said, okay, in each degree we know how to get the invariance, and we know when to stop if it's a finite group. And when to stop is at least not all that big. Okay. Now I want to leave out one more theorem before we take a break. I don't expect you to do anything with this theorem, just it's good to know. So I don't know who exactly to attribute this theorem to. Some people attribute it to Chevalier, Todd, and Shepard, and maybe a more generalized version appears due to Serre. Is if G is a finite group generated by reflections, I shouldn't say, when I say, okay, it's a finite group acting on V. What's the right way to say it? Let's put it this way. If G is a finite subgroup of GLV generated by reflections, then the invariant ring is a polynomial ring. An example of this is this ring of symmetric polynomials. Is a polynomial ring. Okay, what does it really mean? It just means that the elementary symmetric polynomials are algebraically independent. Okay, so I put it in a slightly funny way. I said G is a finite subgroup of GLV. Just because it's a subgroup of GLV, it's acting on V. Kind of a definition, and that's the action that I'm looking for. Okay, so for the symmetric group, you can see that it's a polynomial ring because these things are algebraically independent. And so should that be a polynomial ring? It's a subgroup of the symmetric group. Okay, let's take a break here. So this Reynolds operator that I showed you, which is kind of like you take a sum over all group, translate by the group elements. If you've taken a course on representations of finite groups, you'll notice that this is kind of the trick that you use to prove that any representation can be written as a direct sum of simple representations. Yeah, reductive groups are precisely the groups that have this feature. Any representation is a direct sum of simple representation. A simple representation is one that does not have a sub representation. So,
You mean reducible?
Yeah, irreducible. Cool. Yeah. Okay.
What groups are examples of non-reductive?
Examples of non-reductive groups. This is the thing that we should tell you, right? The complex numbers under addition. Unipotent groups. When I say unipotent groups, I mean things that look like this and something up here. Okay. Now, well, for the same reason, even integers with addition. Okay. Let me see. Can I think of something that's not obviously?
But why is this obvious?
Oh, it's not obvious.
It's not obvious, but it's obviously not for the divergent.
Yeah, it's not obvious, but I will tell you, you can. Okay, so here's one way to do this, right? I told you what reductive is. I said every representation is a direct sum of irreducibles. Here's a representation of this guy, and it's the same for that one. to GL2, and I'm telling you there's a sub-representation without a complement. It's the same reason why this is bad, and it's the same reason why this is bad. I was trying to think of an example where this is not the case, where the bad stuff happened with something else, but I can't at the moment. Okay, so now I want to talk about infinite groups, and I'm going to start with torus. Okay, so I'm going to start with this torus actions. Of course, when I say torus, I mean the complex torus. It's not entirely familiar with you, but the n-dimensional complex torus is just a direct product of C star to the n. Okay. When I say C star, I mean non-zero complex numbers under multiplication as a group, and a direct product of it n times. Why do I consider this group for the first case of infinite is it's an abelian group. Okay. Most of the other stuff that I wrote in that list are not abelian. Okay. This makes things a little bit simpler. So let me do an example, right? This is going to have a slightly different feel to it. I'm not going to just talk about what the invariants are. I'm going to also draw the orbits out, the orbit closures, and so on. Okay. So the example that I'm going to do is my group is going to be the one-dimensional torus, so it's C star, and it's acting on a two-dimensional space. And how does it act? It acts by scaling up x with whatever the number is, and scaling up y with its inverse. Okay. Just a moment to see that this is an action. And because I'm taking C star, I'm allowed to put an inverse in there. Okay. Let's draw a picture. There's good amounts of chalk here. That's can people visualize what the orbit of a certain point is going to be? I claim, okay, so you take some point, okay, 1, 1, right? Then you act upon it with an element of the group. What happens? You go to some other point, but the product of those numbers is always going to be the same. Yeah, and the moment you have two different points whose product of coordinates is the same, you can get from one to the other, almost, assuming none of those coordinates. So this is an orbit for me. So this is an orbit that looks like x times y is some constant, this constant non-zero. Is that clear? If you wish, this is the orbit of C, 1. This should be in white. Sorry. Okay. Now there are some more special looking orbits. I claim the x-axis minus the origin is an orbit. You take 1, 0. Is that what the x-axis is? Yeah. The x-axis is 1, so you take the point 1, 0, and you see where all you can move it to. You can get any multiple of 1 you want, so you can get any t here, and the y is 0, so it doesn't matter. So you're going to get n, 0, a is c, 0. And for the same reason, the y-axis minus the origin is an orbit. And then there's a very special orbit. It's the origin itself. Okay? No matter what group action it is, the origin is always an orbit. This is what it means to be a linear action. Because the group elements are all acting by linear transformations, right? Any linear transformation will preserve the origin. So these are the 4 orbits, and now here's a phenomenon that I want to point out that would not have occurred in finite groups. Okay? And the phenomenon is this orbit is in the closure of this orbit as well as the closure of this orbit. You see that? Okay, so let me put this as 1, 2, 3, 4. 4 is in the closure of 2 and 3. So now I ask, can there be an invariant polynomial that takes different values on 3 and 4? There cannot, right? Why? If you have an invariant polynomial, it's going to take the same value along every point of a certain orbit. So it's going to take the same value along every point of this x-axis minus the origin. So it has to take the same value at the origin. Why? It's a continuous function. At the very least, it's a continuous function. Okay? So here's one feature that you suddenly come across with here's a feature that you suddenly come across is that invariant polynomials may not be able to differentiate between V and W if their orbit closures intersect. Yeah, believe this? This just comes from polynomials being continuous. Cannot. Right? But then here's the theorem of Mumford that everything else is fine. Okay, so the theorem of Mumford says that, okay, so you have your group acting on your vector space, and it's the same things here. Reductive action, it's a reductive group algebraic action. Okay, I won't state it again. Okay, and let's say you take 2 points in this vector space. Then I claim that the orbit closures do not intersect if and only if there exists an invariant polynomial which takes different values in both of them. One side is clear, right? If you have an invariant polynomial that takes different values in both of them, the orbit closures cannot intersect. Yeah, the other way is harder, but it requires certain technical hypotheses which I cannot possibly explain to you in this talk. But you know what groups they are, you know what kind of actions we're looking at. Okay, so let's do this. Okay, is that clear? So now I'm going to define for you this thing called the null cone for the same kind of action. It's going to be the set of points such that 0 is in the orbit closure. We finally get there.
That was a little bit.
Yeah. Okay. Now I want to say, okay, what does it mean for 0 to be in the orbit closure? It really means the orbit closure of 0 and the orbit closure of V do not intersect. Yeah, does that make sense? Because the orbit closure of 0 is just itself, right? So I want to say this is also the 0 locus of non-constant homogeneous invariant polynomials. Okay. As I said, if you have an invariant polynomial, then each homogeneous degree part of it is an invariant polynomial. Okay. So now what I'm trying to say is, if you are able to differentiate something, if you are able to differentiate a point from 0 with an invariant polynomial, Without loss of generality, you can take that invariant polynomial to be homogeneous. Okay? It can't be degree 0 because a constant polynomial will not differentiate anything. So it's going to be some non-constant homogeneous polynomial that's going to differentiate 0 and your point if you were able to differentiate it. Yeah? If you can't, then you are in the 0 locus of all these polynomials because any homogeneous polynomial vanishes on 0. Does that make sense? So this theorem basically gives me this okay, and well, one way to see this is, so one way to interpret this is that this is an analytic definition. It's saying something about look at the orbit and see if the 0 is in the closure or not. This is an algebraic definition. It's saying, okay, just look at whether some polynomials vanish on it or not. And if you go back to the perfect matching case, we had this dichotomy, right? If something had a perfect matching, I was able to drive it down to 0. That's what it means to be in a null cone. And if something didn't, so something didn't have a perfect matching, I could drive it down to 0. And if something did have a perfect matching, then you can't drive it down to 0. But at the same time, you were able to witness this by saying there was a certain invariant polynomial that took a non-zero value on it. Okay?
Zero locus means the place where polynomial has value 0.
Yeah. What are the invariant polynomials here? It's almost staring at you. The product. Okay? So, in this case, the invariant polynomial is just x times y. That's a generator for the ring of invariance. Okay? Now, what is the 0 locus of this polynomial xy? It's the x-axis union y-axis, right? Correct? Which is precisely all those points whose orbit closure contains 0. Do you see that? Any other orbit is away from 0 for precisely this reason. Okay. So I can say there's any number of ways, and I'll keep saying the same thing over and over again. Okay. So now let me see what exactly I wanted to say. Okay. So now what I want to tell you is I want to tell you that null cones for torus actions are connected to linear programming. Okay. So for this I have to tell you a little bit of stuff on torus actions, and we will do this. Okay. So the general setup is my group is going to be an n-dimensional torus, and it's going to act on a vector space, let's say m dimension. Okay. Now I'm going to make one claim. I'm going to make the claim that there exists a basis for this vector space, which let me call V1 to Vm, such that each Vi is a simultaneous eigenvector. For all t in Tn. Do you understand what I'm saying? It's basically saying if you want to look at the action of Tn, there's going to be a particular basis of V. I didn't say anything about it being unique. It's going to be a particular basis of V, so that every element in your torus will act by a diagonal linear transformation. It's just going to scale up each of the bases.
This should be familiar because abelian groups have only one-dimensional representation.
Yeah? This is clear? Okay, but let me, I'm going to use this opportunity to introduce some notation. So each Vi is an eigenvector. So if you multiply it by some element in the torus, you're going to get, okay, so each Vi is an eigenvector, right? So you multiply it by an element in the torus, you're going to get some scalar times Vi. This scalar is going to depend on two things. It's going to depend on this I, and it's going to depend on this function, on this element t. Okay, so I'm going to write as lambda of I of t. So the way I want to think of it is I want to think of lambda of I as a map from Tn to C star.
Maybe it's just notation-wise. Beforehand you used t as a scalar. Now t is an n vector.
Yes, I'm sorry.
That's the same.
T is going to be T1 to Tn. Okay, and why must it be in C star? Because it's a group. It can't kill anything. It has to act by invertible linear transformations, right? Can't kill a vector. Okay, so this is a character of Tn. I hope you've seen this notation. I mean, I'm not saying anything useful. It's just a definition. Let me tell you what all characters of Tn look like. Characters of Tn, you can think of them as in bijection with n tuples of integers. And the bijection is this. If you have some n integers, I will define for you a character that takes T to product of Ti to the Ai. Remember, T is this n tuple T1 to Tn inside this torus. Is that clear? Okay, that's what a character is. So what I want to really claim here is that these m functions, lambda 1 to lambda m, determine everything you want. Okay, that's a claim that you have to believe me. Which one?
The second claim follows from the first claim, right?
More or less. Yeah, the first claim is the harder one. But it's also basic sort of, I mean, the first claim is a linear algebraic claim, really. You can prove that using standard linear algebra. Okay, so let me also make some notation here. Okay, now let's, okay, right. And with this basis, I'm going to take coordinates to be x1 to xn. Is that okay? So from everything I'm going to talk about now on, I'm going to have such a nice basis, such a nice coordinates, and I'm going to work with that basis on coordinates. Okay. So the first claim that I want to make is that a monomial x1 to the Cm, C1 xm to the Cm is invariant if and only if sum of Ci lambda I is equal to 0. And let me remind you, this is an equality in z to the n. Okay, let me prove this for you. You take an element of your torus and you act it on x1 to the cm, xm to the cm. What do you get? Right? What do you get? What does it do to x1? We know what it does to x1. You take lambda 1 of t. Right? So, if you, so let me write it down here. So, t acting on xi is lambda I of t times xi. Okay? So, this is going to be lambda 1 of t x1 to the c1, lambda 2 of t x2 to the c2, lambda m of t xm to the cm. By the way, so I'm going to make this duality, right? So I think of these lambda i's as functions from T n to C star, but I also think of them as elements in Z to the n whenever I want. Okay. Let's write it out. What is lambda 1 of t? It's T1 to the, okay, so it's a bit hard to write. So it's T1 to the lambda 1 sub 1, T2 to the lambda 1 sub 2, Tm to the lambda 1 Tn to the lambda 1 sub n times x1 to the c1 and so on. I'm just expanding it all out, right? Okay. If you think of what this is going to do, the monomial will come out on this side. I will get the monomial here x1 to the c1, xm to the cm, and I'm going to get a scalar here. What's the scalar I get? Okay, let's look at the power of t1. I'm going to get t1 to the power of c1 times lambda 1 sub 1. In the next one, I'd get t1 times c2 times lambda 2 sub 1. Okay, so I'll get t1 to the c1 lambda 1 of 1 plus c2 lambda 2 of 1 cn m lambda m of 1. Okay, times so on all the way up to Tm to the whatever times that. If I want it to be invariant, what do I need? I need this to be 1, right? And these T1 to Tm you can think of as variables because it should be true for all T1 to Tm. That means each one of these powers must be 0, right? So that's the same thing as saying, so if you want this guy to be 1, for all Ti implies sum of Ci lambda I is equal to 0. Yeah, because this is just the same thing as this guy in the first coordinate. Does that make sense? Cool.
I like it in matrix notation. I don't know if you're going to do it.
I will write it in matrix. So let me repackage this. Let me write a matrix that has lambda 1, lambda 2, all the way up to lambda m as columns, right? What am I really asking for? I'm asking for something that's in the kernel of this matrix. Do you see that? A monomial is invariant if that particular exponent vector is in the kernel of this matrix. Okay. So invariant monomials correspond to the kernel of this matrix, but there's a little bit more here. It's not enough to take some exponent vector that's in the kernel. It has, this exponent vector has to have non-negative integers. because it has to be a polynomial, right? I can't have a rational function in there. So intersect with n to the n. You understand? So the way to go from here is to take the exponent vector. Now it's a little bit more here. If you look at this, this is a semigroup under addition. And generators of that semigroup will be the generating invariant monomials. That's kind of some kind of weird linear algebra problem. Right? You have a certain matrix, you want to look at its kernel, you want to look at the non-negative integral points of this kernel. That forms a semigroup. You want to find the generators of the semigroup. Extremely concrete, right? That's what it is. Okay, now what I want to do is I want to quickly talk about the null cone for torus actions. I want to show you why this is the same thing as linear programming. Okay, so let's say you have some element of your vector space and these are its coordinates, right? Yeah.
Can't CIs be in Zn?
No, because I'm looking for polynomials. So something that looks like this is not good for me. I'm looking for polynomial functions that are in
You're
here.
only looking for these coefficients Ci which are in Zn.
Yes.
And this matrix, like you should take any vector V, mv should be 0.
Yeah.
So you look at all such vectors V. And yeah, so why should you look at all Ci which are natural?
Okay, so I want you to go back. When we're looking for invariant polynomials,
Okay.
we're looking for polynomials that are invariant.
Okay.
This is not a polynomial.
Oh, okay. Sure.
Yeah, it's
Oh, I see. So x1 to the c1, xn to the cm have to hold like.
it has to be a polynomial, so the Ci have to be greater than or equal to 0.
So that for any CIs, negative, real, whatever, this will be an invariant function.
Yes.
Oh, that is,
Anything in the kernel will be an invariant function, but we are looking for.
oh, so this is a specific invariant that you're looking at with.
Because we're looking at polynomial invariance.
Oh,
That's the only thing. Okay, so let's go back to the null cone here. You took some point in your vector space. It has coordinates a1 to am. And I want to define the support of a to be all those indices such that ai is not equal to 0. Okay, so a claim. Okay, so something I didn't say because I'm sort of running out of time is that. Oh, I did say it. The generators of this as a semigroup are going to be generators of the invariant ring. Okay, so if you think about this, I have this support. Now, suppose this was whether this was in the null cone or not, I have to decide by saying some invariant monomial is non-zero or not on this. Right? Whatever this invariant monomial, it has to be supported on this support. Otherwise, it's definitely 0. Right? See that? It has to be supported on this, otherwise it's definitely 0. Now, if it is supported on this, now the question basically becomes, can you have an invariant monomial that's supported on this? That's all it really is. If you do have such an invariant monomial, then this cannot be in the null cone because I will take a non-zero value. It will take the corresponding product of those coordinates and it will be something non-zero. Okay? So, A is in the null cone, A is not in the null cone, if and only if there exists invariant monomial supported on this support. What does that mean? That means that you have some linear combination Ci lambda of I is in the support, which is equal to 0. That's what an invariant monomial supported on this looks like. Right? So I should say if and only if there exists Ci such that. That's a linear programming problem, because this is if and only if 0 belongs to the convex hull of lambda I. Okay, when I say there exists Ci, I mean Ci must be greater than or equal to 0. That's a linear programming problem.
Like integer.
Linear program. Yeah? Is that good?
You will not find this in any book on invariant theory. They show it all of this solve functions. I think they consider it.
This was a complaint in one of my papers. They're like, is this theory new? I'm like, no, it's not new. They're like, give me a reference. I'm like, where? Okay, so now I want to go off torus actions. I've demonstrated for you null cones in a bunch of cases. Now I want to talk a little bit about non-commutative identity testing, and this is going to do two things. One is I'm going to relate it back to bipartite matching if I can for a little bit, and it's going to set up what I'm going to talk about next week. Okay. So these things you guys have, I have probably told every one of you a couple of times about these things, but let me just repackage it in a different way. So this is this problem of rational identity testing, right? You have these, something that looks like an expression that involves additions, multiplications, and inverses, and in a non-commutative sense. And you ask whether this expression is 0 or not. Okay? And very formally, this is an expression in what's called the skew field. As always, I won't tell you what the skew field is, but I want to say this is the non-commutative analog of this function field. In what sense is it the non-commutative analog? Let's think about what this is. You start with the complex numbers, and you basically add two variables with no relations. That's what you get the function field, right? You start with the complex numbers, you add two variables with no relations, not even commutativity. Here, when I said no relations, I meant no relations other than commutativity. Here, you don't even ask for commutativity. And you get something. And this object is what's called a skew field. It's called a free skew field. Okay. Skew field is the same thing as a division algebra, which is the same thing as a field where you throw out the axiom of commutativity in multiplication. Okay? And so this is the algorithmic problem where somebody hands you some such expression and they ask you is it 0 or not in this particular field, if you like. Clear? What I'm going to tell you is that this becomes a null cone problem in the following way. So if you have some expression, let's say a formula size S, then you can convert it to a bunch of matrices of size k by k, where k is at most 2s, with the property that r is not equal to 0 is captured precisely by this is not in the null cone, the left right action. Perhaps one thing I should also mention about this torus action is, because I made null cone, okay, so null cone membership is the problem where you say given a point, is it in the null cone or not? It comes down to something that's called linear programming, for which you know efficient algorithms. Okay? So in both examples of null cones that I showed you, it's easy to detect whether something is in the null cone or not. The first example being bipartite matching. Okay? So in the same sort of vein, you have this algorithmic problem, and you find a way to convert it into a null cone membership problem. Right? That's the point here. Of course, I have to tell you what this left-right action is. Let me tell you what this left-right action is.
Yeah, okay. So this doesn't make sense. Why should you optimize only over CIs which are integers? Because you said that you only care about polynomials and variants.
One way to define the null cone is that it's a zero locus of invariant polynomials. If you look for rational functions, it doesn't make too much sense to ask for its zero locus. You also have to worry about where it is not defined and so on.
No, I think he asked why. I mean, it looks like you asked why it is a linear program and not an integer program.
Yeah, why should you not
Because
only care about CIs?
because this
which are-
exists in the solution exists in integers if
Oh.
only if it exists in rationals.
Yeah.
So this
Okay.
happens to be the
Cool.
right. It's allowed.
One has got
No, you don't, because the lambdas are integers. So there is a Russian matter. Yeah, the lambdas are integers. Usually it's discrete. There is a solution in rationals that does more than this solution in integers. It's an
You have to clear denominators, right? You get some linear combination with rational coefficients. Then you just clear denominators, and that will correspond to an invariant monomial. Okay, so let me tell you what this left-right action is. The group is going to be a product of SLNs, right? And it's going to act on m tuples of n by n matrices. And one's going to act on the left, the other is going to act on the right. Okay, and this is the theorem that's due to two different sets of collaborators, Garg, Gurwitz, Oliveira, and Vigdison, and Ivanios, Kyaw, and Subramaniam, is that this null cone membership for this left-right action has a polynomial time algorithm. Okay. There's two things I want to say about this. This is an algebraic action. This is an algebraic algorithm. This is an analytic algorithm. Okay. What does the analytic algorithm do? The analytic algorithm does basically this. It says, okay, I want to know if 0 is in the orbit closure. So I will try to minimize the norm along the orbit and see if I get close to 0 or not. It's a very simple idea, right? If 0 is in the orbit closure, then the minimum of the norm along the orbit must be 0, the infimum. Yeah, so you try to minimize it, and then you run into the part where you have to analyze how quick this algorithm is, what size of step to take in gradient descent or whatever it is. But if you also notice, this is an algorithm that you can apply for any group action. Pretty much, the question becomes some optimization question, right? You just want to see whether 0 is in the orbit closure, so you just try to minimize the norm. Whether you could do it, how hard it is a different story. But in many cases, we seem to be able to do it. And in many cases, we don't know yet. Okay, that's the two things I want to say about this result. But of course, in particular, this captures this problem of rational identity testing, but that also has a polynomial time algorithm. Okay. Now I want to say a few things about this null cone. What do I want to say about this null cone? Let me give a couple of descriptions of this null cone. One that I like.
Before you write, this result, the conversion of rational expressions to a bunch of matrices should be familiar to you. Or from polynomials to formulas to a bunch of matrices.
Valiant.
Yeah. So it's the same as what this result of Cone from 1970, so way before Valiant, which proves the more general result of Valiant because it's the same construction which works actually in the non-commutative set and therefore works also in the commutative set. That's what Valiant did normally.
randomized algorithms to check whether they are identically zero or not.
Yes.
But what about the if you
Well, now we have a
take-
polynomial time algorithm, so
No,
but the randomized algorithm is slightly easier than the polynomial time algorithm.
but it's not simple to explain.
It is simple to explain. You plug in, so if your formula size was S, you plug in random 2S by 2S matrices. That's the algorithm. Okay, so there's two things I want to say. The first is that I want to talk about this null cone for the left-right action, and I want to give it two descriptions. And when I say two descriptions, I mean other than the defining description that all points whose orbit closure contains 0. Yeah, so two descriptions. The first one is x. Okay, so let's see what I'm saying. So I have an M tuple is in the null cone if and only if there exists p comma q in SLN cross SLN such that p xi q belongs to something like this, where if this is size beta, that's size alpha, alpha plus beta is less than n. Okay. Now, what am I saying? I'm saying something is in the null cone if and only if you could change it with some element of the group action to get it into a form where you have a big block of zeros for all I simultaneously. Okay. What does this big block of zeros remind you of? It reminds you of Hall's theorem, right? What is the action in the Hall's theorem? It was STN cross STN. So what is this saying? This is saying you're in the null cone for the SLN cross SLN if up to some element, some action of some particular element in the group, you are in the null cone for the STN cross STN action. Okay. This is a theorem, and it's called the Hilbert-Mumford criterion, and it's even more general, and I will state it in this greater generality because I'm going to use it at some point. So G is a reductive group. It's acting on some vector space. T is what I call a maximal torus of G. I will explain this. Then I claim the null cone for the action of G is you take the null cone for the action of T and you move it around by the group. Okay. Before you think about what these terms mean, if you take G to be SLN cross SLN and T to be STN cross STN, you see that that's what this statement is. Right? You took the null cone for STN cross STN, which is basically everything that looks like that, and then move it around by the group. Okay? In general, you take a reductive group, it has what's called a maximal torus. It's a very silly definition. What's a maximal torus? The largest subgroup of G that looks like a torus. Okay? It's you could have a finite group that's abelian. Maximal connected abelian subgroup. Okay? So, well, of course, what you're missing is that there's structure theorems for reductive groups that tell you that maximal tori are pretty large inside this group and so on. But once you can find them, in this case, you know what it is. For SLN, it would be STN, and for GLN, it would just be the diagonal matrices. That's pretty much all you really need to know. Anytime you have a matrix group, just restrict yourself to the diagonal matrices, and that will be more or less your maximal torus. Okay. So what this is saying if you want to understand the null cone for the group, you understand the null cone for the maximal torus and move it around by the group. Okay. Null cone for torus actions is not so hard. Okay. But of course, you're stuck in this point where you are able to describe this null cone up to like some sort of change of basis, which is not always easy to capture, right? How do you know which basis to pick before you see this particular pattern or whatever it is? Okay. So that's the problem that you come across. This case. Now let me give you another description of this particular null cone. The other way to describe this null cone is to write it as the set of all tuples x1 to xn, m tuples of matrices, such that sum of ti xi is singular over this free skew field. Okay. So, two words about this. I take a formal linear combination of these matrices, right? Now, elements in this particular linear combination are linear expressions in T1 to Tm with coefficients and complex numbers. I can think of those as elements in this free skew field, right? I can think of them. Now, what does it mean for such a matrix to be singular? Basically, you can do linear algebra over a skew field. You can do linear algebra over a division ring, exactly the same way you do as linear algebra over a field. The only difference is you do not have what's called a determinant, or at least it doesn't work the way you want it to. But then how can you define rank? You define it as the column rank, where you allow linear combinations by multiplying with scalars on the left, let's say. Okay. Now, that should remind you a little bit more of Valiant's construction of completeness of determinant or whatever it is. Okay. Now, my claim is that this is equal to the null cone for the left-right action. But this also captures this problem of rational identity testing. Right? Yeah? Okay. Now, I am going to define another variety that I call singular tuples of matrices, which is going to look exactly the same, except I now live in the commutative world rather than the non-commutative world. Yeah, it's exactly the same looking thing. And the claim is this captures polynomial identity testing. Or rather, let me write it as symbolic determinant identity testing, which is equivalent to the polynomial identity testing, more or less. Okay. In this case, it's much easier. If you want to find whether such a matrix is singular or not, you can just take the determinant and see whether it's 0 or not. That's a symbolic determinant of a matrix with linear entries. Okay. That's the problem of symbolic determinant identity testing, which is equivalent to this problem of polynomial identity testing. Okay. And now, what do you know? You know that polynomial identity testing, if you gave a polynomial time algorithm for it, this would imply by Cabonet's Impagliazzo, I don't know what's the right. I would say something close to P versus NP, but will imply non-trivial lower bounds. Okay. So now comes the question. You look at this. You look at this set. You look at this set. They look exactly the same.
Will it imply non-trivial lower bounds, or imply non-trivial, like imply something we don't believe?
Yeah, ask.
What's the question?
Like if PID belongs to P, is it something we don't believe, or
We believe, right? We believe.
Oh, we
sure,
believe.
because no, we believe it means I believe. Everything that you can do with randomness, you can do with that. Okay, but yeah, I don't know how general this belief, but look what it implies. It implies VP different than VNP, or that next is not in polynomial. In P/slash poly, these are surely we should believe. Anyway, yeah. So you should say maybe Cabonet's Impagliazzo also prove the reverse, right? They prove that the VP is different than VP.
Oh, I see.
Than PID and P, right? So it's really an equivalence. If you spell out some of the, it's sort of,
Almost an
right,
equivalence.
sort of.
I don't remember the proof for this theorem, but
which direction are you asking about? The direction up is like that.
So
Yeah.
this is like a very specific problem in BPP.
That's right. Yeah, it's a very specific problem in BPP. It's sort of amazing. I mean, nobody it was a sort of shock when they proved it, even though the proof is very simple. That de-randomizing a very, very special problem in BPP already implies non-trivial Lorban. Yes, and taking it back allows it to to de-randomize practically everything, but it's not exactly that strong.
Okay. So the upshot of that conversation is that you really, really want to prove a polynomial time algorithm for PIT. Okay. If you look at the non-commutative version of it, you were able to prove a polynomial time algorithm, and that came as what? You proved a certain variety was equal to the null cone and used everything you knew about the null cone. Okay. Here comes the question. Wouldn't it be nice if this were a null cone for some group action? Is this a null cone for some group action? It's not a question that people usually ask. You've gone backwards, right? I give you some variety, and I ask you, is it the null cone for some group action? In which case, I'm asking you, can you present me a group whose null cone is this guy? And if you can't, can you tell me that you can't? Okay? That's going to be next week's talk.